Welcome to the deep dive. Today, we are taking you straight into the engine room of hardware development. We're looking at a real paradigm shift here, one that's cracking open these highly specialized, proprietary, sort of walled gardens of silicon design and pulling a whole field into the open source community. Our sources today are all focused on the FPGA ecosystem. You might have known it as SymbiFlow, and its mission to democratize hardware. We're going to be analyzing how this new approach, this new flow, really changes the game for engineers programming physical hardware circuitry on FPGAs.
Yeah,
Because historically, this has been a very high-cost, high barrier to entry world.
it really was. And our deep dive today is all about understanding the core tension at play here. You have this choice, between the traditional vendor tools that promise maximum super optimized performance
Right.
versus this newer open source approach that's all about flexibility, transparency, and maybe most critically, iteration speed. We're seeing this powerful pivot where the community is often choosing those values over raw clock speed.
Okay, so let's unpack this. To really get it, we should probably start by establishing the old constraints. What were the big structural barriers that made working with FPGAs so, I guess, frustrating and inaccessible when you had to rely on those closed source tools from the chip makers?
Well, historically, engineers were dealing with what the sources break down into four major roadblocks. The first and maybe the most obvious one was vendor lock-in. The tool chain, the entire suite of software you need to turn your design into a working chip was completely tied to one manufacturer's specific device family.
Ah, okay.
So if you invested all this time and money training your team on, say, the Xilinx suite, and then you wanted to move to a Lattice chip,
You had to scrap everything and start over.
exactly, you'd scrap that institutional knowledge and begin from square one with a totally new software environment. That lack of portability was a massive restriction on your technical freedom.
Which I'm guessing creates a monopoly situation that leads straight to the second barrier,
Mhm.
the cost.
High cost, precisely. If the vendor has you locked in, they can pretty much set the price for the software license.
Right.
And we saw these substantial recurring licensing fees that acted as this huge form of financial gatekeeping. It wasn't just tough on like a small startup, it created an enormous obstacle for academic institutions, for individual researchers.
If you couldn't find a few $1,000s for the annual license,
You were just out. You simply couldn't participate in cutting edge FPGA research. End of story.
and the third barrier really hits at the heart of engineering itself, the lack of transparency. This is what the sources are calling the black box problem.
That's right. So imagine you're a researcher focused on computer-aided design, on CAD, and you think you have a better, faster algorithm for placing circuits on a chip.
You can't test it.
You can't. The inner workings of the synthesis tools, the place and route algorithms, they were all proprietary secrets. It's like being a software engineer, but you're forbidden from ever seeing the source code of the compiler.
Yeah, that's a good analogy.
That black box actively choked community innovation because no one could experiment with the fundamental tools of the trade.
Which brings us to the fourth problem,
Mm.
which is a practical one. Slow iteration. These big proprietary tools were often optimized for massive designs, but for small changes, they were just brutally slow.
Yes, and this is a pacing problem, a huge one. Proprietary tools could take minutes or, even hours for a single full build cycle.
Hours for one build.
Oh, yeah. So if you're trying to debug a tricky timing issue and every little change you make takes 5 hours to test, it's less like engineering and more like watching paint dry. It's a total death blow to rapid development.
So, okay, we have cost, control, and obscurity creating this monopoly. The only way to break that, it seems, is through a total system reset. So how does this F4PGA ecosystem step in to fix all that?
Well, the core mission of F4PGA is, it's pretty profound. It's to create a collaborative, vendor-neutral, and transparent platform that completely democratizes hardware design. The goal is to be the standard open source flow.
Taking the power back from the manufacturer,
Yeah.
basically.
Exactly. And it's built on three main pillars. First, it's free and open source, no license fees. You can see all the guide. Second, it's aggressively vendor neutral. The tools target FPGAs from multiple makers, Xilinx, Lattice, QuickLogic,
So portable.
totally portable. And third, the tools are modular and extensible. It's a suite of interchangeable parts that the community can continuously improve one piece at a time.
And that's why people have started calling it the GCC of FPGAs, which is just a fantastic parallel. For anyone listening who isn't deep in software, GCC is the standard open source compiler. It's the engine that makes so much of modern software possible.
It is. And FPGA wants to be that same stable, universal foundation for hardware. It means the IP you create lives outside the control of any single chip vendor.
So let's get into the mechanics. Walk us through the anatomy of this open source flow. What are the main stages?
Okay, so the flow starts with the hardware description. This is where you write your logic, usually in, classic languages like Verilog or VHDL.
But new options are popping up too, right?
Yeah, increasingly, engineers are using modern Python-based approaches like Amaranth, which gives you better scripting and, frankly, more reliability. That description then moves into stage 2, synthesis. This is handled by a core tool called Yosis. Yosis takes your high-level code, your RTL, and transforms it into what's called a technology-mapped netlist. It's a really robust tool.
Okay, so once the logic's all mapped out virtually, we have to make it physical. Step 3.
That netlist then goes into the place and route stage. This is handled by tools like NextPNR or VTR. And this is the critical step where the software decides exactly where each logic gate will sit on the physical FPGA grid.
And then connects all the dots.
And routes the millions of connections between them. It's like designing a massive, city-wide subway system on a tiny piece of silicon. Finally, that placed and routed design goes through bitstream generation. This converts the whole thing into the binary file, the ones and zeros that you actually download to configure the FPGA hardware.
That flow makes sense. But it brings us to the fundamental mystery here. The vendors guard their chip architectures so closely. So how do these open source tools know how to talk to closed source hardware at all?
This is the real secret sauce. And it's just a heroic effort in community-driven reverse engineering. The technique is called data-driven FPGA architecture definitions.
Okay, what does that mean?
Well, since the vendors won't share the blueprints, the community just decided to build their own maps.
Wow.
Systematically. They run thousands of tiny, simple Verilog designs through the official vendor tools. I'm talking tests that might only use a single logic gate or connect one wire. Then they capture the bitstream file that the tool spits out, and they meticulously analyze that output bit by bit. Through statistical analysis, they figure out which specific bit in that binary file controls which tiny little function on the chip.
Wow. The amount of labor just to map one chip architecture bit by bit must be absolutely staggering.
It is. The sources basically describe these engineers as digital archaeologists, and the foundational projects are amazing. Project Ice Storm successfully documented the Lattice ICE40 family. Project Trellis did the more complex Lattice ECP5.
And there's one for Xilinx, too.
Yeah, the really monumental one is Project X-Ray, which is tackling the incredibly intricate Xilinx 7 series architecture. Without these reverse-engineered maps, none of the open-source tools could function.
Okay, the mechanism is clear now. So let's get to the first critical verdict, the trade-off. What's the single most compelling reason people are adopting this flow, and what's the price they pay for it?
The killer feature, hands down, is iteration speed. The data on this is just overwhelming. The open source flow completely transforms the development cycle. Full synthesis and implementation can happen in seconds.
The seconds.
Yeah, we're talking benchmarks that frequently clock in under 1 minute. The sources cite an example of 28 seconds.
And what's the proprietary comparison for that 28-second turnaround?
Well, a proprietary tool like Xilinx Vivado commonly takes 5 minutes for even the simplest builds, and it can easily push into several hours for complex systems.
So it's not even close.
Not at all. The sources note that a design on an ECP5 using Yosis and NextPNR takes less than 30 seconds, where a similar design on an Arctic 7 in Vivado takes at least 5 minutes. This speed is a game changer. It's what finally makes automated hardware testing, CI/CD, actually viable.
Okay, but wait. If the proprietary tools take that much longer, it must be because they're searching for the absolute best optimization, right?
Correct.
So we have to be paying a price for that speed. What's the hit to the quality of results, the QRR?
That is the crucial strategic trade-off, and we have specific data on this, comparing the FOSS flow against Vivado on an Arctic 7. So yes, the open source flow is way faster. The total tool runtime is 0.45x, so less than half the time.
Right.
But the quality metrics show the penalty. First, logic utilization is 2.08x, meaning the open source tools are much less efficient at packing the logic onto the chip. This is a huge penalty. It could mean your design doesn't fit on the chip you bought, or you have to buy a bigger, more expensive device just to make it work.
So that's a direct economic constraint, not just a technical one.
Absolutely. And the second penalty is performance. The critical path delay is 2.27 times longer.
Whoa, okay, stop. 7 times longer. That means your max clock speed is less than half.
Yeah.
Isn't that a catastrophic failure for most systems? Who would ever accept that?
You'd think so, right? But this is where the strategic choice comes in. The proprietary tools are built for applications that absolutely must have peak performance, think 5G backhaul or high frequency trading. They are chasing the highest possible clock speed, and they don't care if it takes 5 hours to compile.
Okay.
But for huge segments of the market prototyping, a lot of embedded systems where the clock speed you need is pretty modest, educational platforms, that 5 hours of waiting is the bigger penalty.
I see.
For an engineer iterating 20 times a day to fix a bug, trading a 2.27x speed hit for a, 100-fold increase in daily iteration capacity, that's an incredibly powerful engineering decision. The FOSS flow prioritizes flexibility and speed over peak performance.
So based on that trade-off, where is open source really excelling today? Where are people making that choice?
The advantages really fall into four key buckets. First, academia and CAD research. Because the tools are transparent, researchers can experiment with totally new algorithms and tool chains like VTR. That was impossible before. Second, rapid prototyping and CI/CD. We talked about this. Those sub-minute compile times are just essential for automated hardware testing workflows.
And the third area seems core to the whole spirit of this, open IP development.
Exactly. This ecosystem is the perfect home for developing and verifying portable open source IP cores, like the popular RISC-V P-Core V32 processor. This IP isn't tied to a vendor. It works wherever the FOSS flow works. And the fourth, which might be the most significant, is commercial production, but for specific devices. For companies building products on the really well-supported Lattice ICE40 and ECP5 families, vendor independence is a huge commercial advantage.
Can you break that down? Why is that independence so valuable in a business sense?
Well, for commercial users, it means you're immune to vendor price hikes on software, or sudden end-of-life announcements for a chip you rely on, or even restrictive licensing changes. You control your entire tool chain. That gives you supply chain resilience and really long-term business security.
Speaking of support, let's look at maturity. The architectural support matrix in the sources makes it pretty clear that not all FPGAs are ready for prime time yet.
That's a key detail you need to understand, yeah. The Lattice families, thanks to Project Ice Storm and Trellis, offer the most complete production-ready experience. They fully support core logic, the on-chip block RAM, and even the specialized math units, the DSP slices.
But the more complex chips are lagging behind.
They are. When you look at the Xilinx 7 series from Project X-Ray, the reverse engineering is still catching up. High-speed I/O like SerDes, those blocks that handle multi-gigabit data streams or PCIe, they're still marked as experimental or unsupported. Their complexity just makes them exponentially harder to map out.
So if your product needs cutting-edge high-speed networking, you're probably still locked in to the proprietary tools for now.
For now, yes. But for general computing logic and the majority of embedded applications, the open source path is fully viable today, and the usability is improving dramatically. Earlier flows were tricky. You needed complex command line scripts. But now, the FPGA Python package has emerged to provide a unified command line interface and a proper build system. It just simplifies everything. And it's not just the core flow, the whole surrounding ecosystem is thriving. You've got high-level languages like Amaranth and Chisel and professional simulation tools like Verilator and VUnit, which are essential for any robust design.
So we've analyzed the trade-off, speed and flexibility over peak performance. We understand the reverse engineering secret sauce. What does the road ahead look like for the FPGA community?
The whole ecosystem is just accelerating. The work is continuous. We're seeing active development for broader device. Support Next PNR is adding support for newer architectures like Lattice Nexus and Go and Little B.
And what about that performance gap?
They're focused on it intensely, improving QRR. There's active work in VPR and Next PNR to enhance the timing-driven algorithms, which means that 2.27x slower speed gap is constantly shrinking. And, of course, the ongoing work in projects like X-Ray to enable complex hard IP is key to unlocking full functionality on those advanced high-speed blocks.
This really does feel like a fundamental paradigm shift, one that's going to accelerate hardware innovation. You now have a deep understanding of why hardware developers are strategically choosing to trade peak optimization for radical flexibility and speed. We started this deep dive talking about how open source tech revolutionized the software world, democratizing everything from operating systems to the cloud. So here's the provocative thought for you to chew on. If vendor-independent, transparent, and rapidly iterable open source hardware tools become the dominant standard, especially for new things like RISC-V, what proprietary design secrets will the community unlock next? And who benefits most when the black box's silicon is finally documented and open to everyone?